let me go to you guys, limits, and also we're going to study today what's called continuity. This is another important idea of calculus, continuity. So I'm going to take a few problems right from your book and work them out, and I think this will be a nice intro to the subject. So the first I picked was problem 14 from your book. They give you a function. It's a function that is called a rational function. What I mean by that is I have a polynomial. Actually, what kind of polynomial? If you had to graph just the numerator, what is that? Just the numerator piece. That's a parabola, right? It's quadratic. And in the denominator, you have another parabola. But now you're dividing them. This is called a rational function. I know here at Lakeland, we studied these in college algebra. Okay. And I'm giving you a value for the letter A. That's the letter that's used in our book most often. And I'm going to compute for you a limit. Okay? In order to kind of explain what's going on. Now, by the way, I have a question. Is it possible to compute f of 3? I'm hearing yes, I'm hearing no. Well, that's interesting.
Oh, no. You have a denominator of 0.
If we plug in a 3 right now, right, we say we can't. We have a denominator of 0. Okay? So, I mean, one of the first things I'm going to point out to you guys, and again, this may be an algebra idea, is that notice three is not in the domain. What's the word domain mean? Set of all possible, inputs, I like to say, the values that go in for x. 3 is not in the domain, so we cannot compute f of 3. So now here's a question. We're not supposed to compute f of 3 in this problem. What they're asking me to compute is the limit as x approaches 3 of f of x. That's what I'm trying to compute. Right? So what does that equal? Well, it's the limit as x approaches 3. And I'm going to write down the fraction. But I don't know about you. Well, let's write it down. X squared minus 3x over x squared minus 9. Let's do that. And let's take the calculator out to help. I'd like to type that function into my calculator, and I'd like you to do it too if you have one. So I'm going to go ahead and pause the recording and then come back once I have my x squared minus 3x in parentheses. I'm going to divide by, and I'll open parentheses, x squared minus 9. If I don't have those parentheses, it's not going to work. Close parentheses. Hey, I'm going to go ahead and sketch a graph. Oh, wait a minute. If I graph it now, I'm not going to be able to see it, right? Because that window was for the last problem. Let me click on Zoom, and I'm going to choose choice 6, just the standard zoom from -10 to +10, and now I can kind of see my picture. Okay? It's an interesting picture, interesting graph. Remember I asked you guys, can you compute f of 3?
No.
Does it look like f of 3 is there?
No.
Why do you say no? Oh, you're looking at the asymptote. How many people remember asymptotes from algebra class? Okay, but here's the thing though, that asymptote, isn't that at -3? I think that asymptote's at -3. And I was talking about +3. +3 is over here. Some of you are going to try doing the calculate feature that I did earlier, and you'll see it doesn't work. But let me do this, though. Another feature that we have is called the table. And I believe that's right above where it says graph. See it says table there? let's go ahead and write second graph here. So I'm going to get a table generated. And sure enough, I can compute f of 0, I can compute f of 1, right? You know what this looks like? This is like when you're in algebra class and you're first learning how to sketch graphs, right? You did plotting points. You would have x and f of x, right? And so I have 0, 0. F of 0 is 0. F of 1 is 1/4. F of 2 is, it says 0.4. Do you know what fraction that is? 2/5, yeah. F of 3, we don't know. It's undefined, I'll say. They put error. F of 4, what's it say? 0.57 something? Okay. And F of 5 is 0.625. So this was 0.4, and this was undefined, and this is about 0.57. So it's interesting. This function is not defined for 3. And by the way, it's also not defined for -3. You were right about that. If I hit the up arrow, I can look at some of the negative values. Notice there's an error for -3 also. Okay? But let's go back down and look at 3, because that's what I'm most interested in. The first thing that our book does to help you understand the idea of limits is they start generating tables, kind of like what I have here, kind of like this. But we're going to do things a little bit differently. Let me just go back to the regular screen for a minute. No, let me go to the graph. That was nicer. Because then I can do second calculate, and I can throw in some different values. Okay. When we compute the limit as x approaches 3, I want you to understand, we do not compute f of 3. Instead, we are interested in what happens as x approaches 3. When x gets close to 3, that's what we're interested in. Does that make sense to you guys? Not yet, maybe. Well, let me do this. I'm going to go ahead and write down the fact. I'm going to take this chart, but I'm going to rearrange it so that it's horizontal so I can represent things maybe a little better. So I'm still going to put x and f of x, but I'm going to write them as rows rather than as columns. And you'll see these charts in the book. And right in the middle here where it says x, let me write 3 and write undefined. So for 3, it's undefined. Over here, we know that if we have a value of 4, the output is 0.57. Or if we have an output of 2, an input of 2, the output is 0.4. Okay? So I guess what I'm interested in is what happens in between those values. In between x equals 2 and x equals 4. So I'm going to take a value a little bigger than 2. Why don't I take 2.5? Let's compute what that is. See what I get. Guys have an answer? Well, I could put 2.5 in the calculator and find out that it's, what do we have? 454545. 0.45 repeating, if you want, right? I can get even closer to 3. I could say 2.9. And if I throw in 2.9, enter. Now where am I at? 0.492 or so. 4915, right? I can get even closer, 2.99. Let me do another one, 9. That's really close to 3, isn't it? Is f of 2.999 defined?
Yes.
Sure, you could plug that in. Let's do it. 2.999. Enter. What's the output very close to?
0.5.
Very close to 0.5. You guys with me? Now that's what you might call the left-hand limit. I came from the left side. We could do the same thing coming from the right side. So give me a number between 3 and 4. 3.1 is a nice choice. Let's do 3.1. What do we get? 0.50. You know, that's already pretty close to 0.5. Would you guys believe me at this point if I told you that this limit, for some reason, equals 1/2? Does that make sense? What am I trying to say? We don't compute f of 3. F of 3 is undefined. We are interested in what happens as x approaches 3. As x gets close to 3, the outputs are getting close to what? 1/2, 0.5. That's right. That's what we say the limit is. To do it a little more, let's take a number even closer to 3. 3.01. Do I get closer to 1/2?
Yeah.
And if you take a number even closer to 3, like a seal number, you're going to get very close. So could someone give me a seal number? You guys know what seal numbers are, right? How many have never heard of seal numbers? Really? You guys came from, I saw where you guys took that. All right. Let's put it this way. Give me a number closer to 3 than 3.01. Who has one? Go ahead, go ahead.
3.000.
Stand up so everyone can hear this.
3.00.
No, you had it right the first time.
3.001.
Yeah, but like this. Hold your arms out like this. Try again.
3.000.
Oh, I get it.
A seal number. 3.0001. Now, so thank you. 3.0001. If you have a seal number, we're going to be incredibly close to the limit. 0.500, right? So, did we learn anything? I don't know. Stupid sense of humor. But the point is that we will say that the limit is 1/2. I just showed this numerically. Okay? This is a numerical approach. I guess I also showed you a graphical approach. I showed you on the picture that we're getting very close to 1/2. But what we also want is we want an analytical approach. And so I want to revisit the problem one more time here. I'm going to move to the next page here if you guys are ready. Is this okay? Let's write the problem down one more time. And let's apply our analytic skills we learned from algebra class, even if we didn't ever learn what a seal number was. My goodness. So limit as x approaches 3, and the problem was x squared minus 3x over x minus 9. X squared minus 9. Thank you. And for any of you, didn't your algebra instincts just kick in when you saw the x squared minus 9? What did you want to do immediately? You wanted to factor it because you've been well trained. You factor it how? X minus 3 times x plus 3. And what about that numerator? Can that be factored?
E take x.
We can take out that x. And we get x times what?
X minus 3.
X minus 3. Now, this is a nice little trick.
Cross out, cross multiply?
It's not cross multiplying, but it is crossing out, yeah, or canceling. When everything is factored, you can cancel. And so what we're going to cancel here are the common factors, x minus 3, x minus 3. So I'm going to say that this limit is equal to the limit as x approaches 3 of x over x plus 3. And so what do I get? Well, at this point, okay, I'm going to say, because I know something, I'll explain what I know in a minute, okay, I can just take the 3 and I can substitute in. It'll work now, won't it? What do you get?
1.
You get 3 over 3 plus 3, 3 over 6. Sure enough, the limit is 1/2.
Genius.
Okay? But I knew something there. What did I know? Well, I guess I knew,
The limit.
yeah, I knew the trick, first of all, to factor and cancel. But I also knew something about this function compared to the original function. And that is that the graphs are almost the same. Let me show you. Go to the y equals screen for a minute. And I guess I'll save this one in case I want it. I'll click enter. So I'll just turn off the function for a little bit. But over here, let me just type in x divided by parentheses x plus 3. And I want you to notice what the graph of this guy looks like. Do you notice any difference? No. That's because there's only one difference on the entire graph. The only difference that this graph has compared to the one before it, you'll notice if you try to calculate the value at 3, can you do that now? That's what I just did. So they're the same function except that this one is, and the word is, continuous at x equals 3. I know this function is continuous at x equals 3. And when I know the function's continuous, I can go ahead and substitute in. Question?
Okay, so so when we're doing this and we get the equation, we get the answer. So basically, the answer we're getting is the answer that we will never be able to get. Yeah.
So
Seems like
yeah,
it's-
using the word answer is going to get you in trouble.
Okay.
Okay? What is it we computed? We computed the limit. Let's use the word.
Okay.
We cannot compute f of 3. But we can compute in this problem the limit. Okay? Does that make sense?
Yeah.
Hey, by the way, it doesn't always work. It doesn't always work. What would happen if I said, let's compute the limit as x approaches -3 of this thing? Yeah, it does not exist. How do you see that? Well, maybe the best way to see it is graphically. See, we have two different phenomena. So let me write down a little fact for you. Actually, I have it here on the PowerPoint, I think, that kind of explains what's going on. This one I'll do in a minute. Oh, the definition of continuity. Yeah, okay, think, Paul, for a minute. So if I have a piecewise defined function, and let me write it down, f of x equals x squared plus 1, and I know you can't see my little thing quite yet, where x is greater than or equal to 0, or 2x squared minus 1 when x is less than 0. But I'm going to go ahead and let you look at that. So, what does this function look like? Well, it's just defined in pieces. If I were going to sketch the graph, okay, I know that when x is bigger than or equal to 0, I'm talking about the parabola x squared plus 1. Does that open upward or downward? And x squared plus 1, it starts, say, at 0, 1, and it opens upward, right? But what about this piece? When x is less than 0, well, that's a parabola also opening upward, but what's going to be true about it? It starts at negative 1. I'm going to put an open circle at negative 1 because really we're only on this curve, which is a steeper parabola, by the way. The 2 makes it steeper. We're only on the red curve when x is less than 0, right? If you were to graph the whole parabola, it would have a mirror image. You guys remember that? But this is a picture of the function I'm talking about in number 18. Okay? And I might ask you guys, what's my a value we said? A equals 0. Yeah, see, a is the interesting point. Is f of a defined? F of 0 equals what? 1. Yeah, because it says greater than or equal to 0, you're in this top line. F of 0 equals 1. You guys got that? But if I said, let's find the limit as x approaches 0 of f of x, in this problem I have to say it does not exist. Why? Because the function is not continuous. There's that word again. I'm about to give you the definition of continuous. But let me say a little more, okay? For the limit as x approaches a of f of x to exist, we need the following. The limit as x approaches a from the negative side has to equal the limit as x approaches a from the positive side. This is a nice fact to know, what I just wrote in blue. Let me explain using the picture. In this problem, the limit as x approaches 0 from the positive side of f of x, that's 1. Because I could play the same game with my calculator. Give me a seal number very close to 0. The outputs would be very close to 1. But if I take the limit as x approaches 0 from the negative side of f of x in this problem, what do you guys think that equals? Yeah, the outputs get very close to negative 1 because that's the value 0, negative 1. You guys with me?
Can you explain that again?
Well, give me a negative number.
Negative 2.
Negative 2. If I plug in negative 2 and wanted to compute it, how would you do it? F of negative 2. would you use the x squared plus 1 or would you use the 2x squared minus 1? Since x is less than 0, I would use
2x squared.
the 2 times negative 2 squared minus 1, right? 2 times 4 minus 1. So it's 8 minus 1 is 7. Okay? So that's up here. 2 comma, negative 2 comma 7. Negative 2 comma 7 is a point on the graph. Well, if you picked something close to 0, you'd be moving along the curve as you get close to 0. The outputs would get close to what? Negative 1. That's called the, if you want, left-hand limit. Whereas this one's called, what do you think that's called? The right-hand limit. Okay? So the fact says, the fact in the box says, for the limit to exist, we need the left-hand limit to equal the right-hand limit. This is a function that doesn't have that, so the limit does not exist.
So it doesn't have a right-hand limit?
It has a right-hand limit. What is the right-hand limit? Positive 1. As I come in from the positive side, I'm getting towards 1.
Mm-hmm.
As I come in from the negative side, I get towards negative 1. Okay? This is something to look out for. We would say the function is not continuous. And that's really what the next sheet of paper ought to be about here. Question?
Would we immediately know that the limit does not exist for this one, since you can put 0 into this function and have an output?
No, we don't know that. Maybe the limit exists. The limit doesn't really have anything to do with whether the function exists or not. The limit is talking about what happens when you're close to that x value, close to a. All right? So now I'm ready to talk about continuity. Continuity, the idea is I can graph without picking up my pencil. Is that okay? So the last picture that I had up there, could I do that? No, I had to pick up. I was on the red curve and then the black curve, right? We saw that. Right? So that was an example of a function that's not continuous. But we need a better definition than this. That's why it's in quotes. And so here's the definition that I will use. Definition. The function f of x is continuous at x equals a. If I say that, this means that the limit as x approaches a of f of x equals f of a. That's my definition. And for the last 5 minutes of class, I'm going to try and give you lots of examples that demonstrates how the definition can work and how it doesn't work. And the relationship. You can see why we studied limits, right? If you want to talk about a function being continuous, you have to not only look at the values of the function, but you have to look at the limit. So my claim is that this is really 3 statements in one. Because for that equation to be true, first of all, f of a has to be defined, right? Otherwise, the equation wouldn't make sense. For example, take that function. I would say this function is not continuous where? At x equals 4. Because it's not even defined. So how am I going to satisfy that equation if the right-hand side, f of a, is not even defined? You guys with me?
You can factor it out.
Well, yeah, but this function will not be continuous at 4. It's interesting you said factor it out, because what is true is that the limit exists. That's what you're showing me. Let me do that real quick, because that was a good idea. So the function was f of x equals, was it x squared minus 16 over what?
X minus 4.
Okay. And so what we just said is that f of 4 is undefined. Right? So we already blew it. It's not continuous. You can't talk about f of a in this example. A is 4. But what your idea was, let's factor it. What we can do in this problem is the left-hand side. We can compute the limit as x approaches what? 4 of x squared minus 16 over x minus 4. How do you do it? You write the limit as x approaches 4 of, what would we write that numerator as? X minus 4, x plus 4, all over x minus 4. Cancel them out. This is the limit as x approaches 4 of just x plus 4. Do you know what it equals?
The limit is 8.
It's 8. 4 plus 4 is 8. And if you were to graph that function on the calculator, you would see the values get very close to 8 when x is close to 4. Does that make sense? There would be a hole in the graph at the point 4, 8, in a sense. Okay? Does this make sense to you guys? So, moving on, talk about continuity. F of a has to be defined, but also the limit has to exist. Okay? So here's another function that I'm going to put on the board. This is piecewise defined. All right, guys. Does the limit exist? We just computed it, right?
Yeah.
Okay. Well, what's the limit as x approaches 4?
8.
We said it's 8. Is f of a defined? Again, here a is 4. Is f of 4 defined for this function?
No.
I claim yes. Because when x equals 4, which line of the function am I supposed to be looking at? The second line, right? So what is f of 4 for that example? 4. Well, that's no good. For this function, so here's my new example. I'll do it in blue. Suppose f of x equals either x squared minus 16 over x minus 4, or just equals 4 when x is 4 or when x does not equal 4. This function is not continuous either. Why? Well, does the limit exist? Yeah, the limit equals 8. Does f of a exist? Yeah, that's this line. 4, we said the output is. Are these equal? No. You need those to be equal to be continuous. See, that's why I said there's really 3 statements in one. They both have to exist. They have to be equal. So if you want a continuous function, how about that one? That function would work. See, the graph of this function, x squared minus 16 over x minus 4, it's worth looking at. And then we're out of here. X squared minus 16 over x minus 4. And let me clear this out. And let me hit graph. Hey, that function doesn't look all that special. Okay? But the only thing is, if you hit like table, you can see that 4 is an error. You guys with me? But if I define the output of 4 to be 8, do you see how it kind of fills in the missing point? That makes it continuous.
So that's what you're saying it's defined, that it has a limit?
No, I defined it by this 8 right here. I defined it. I told you when x is 4, the output's 8. Kind of made it up.
That was when like we did the factoring and stuff. That's how you got that, or how did
Well,
you say?
the limit is 8.
Yeah.
That's from the factoring, and that's 8. We'll do more next week, guys.
Can you switch back to your notes?
Sure.
Do you have anything to do as a class?
So, when we were talking about limits, we didn't mention this idea, or maybe I mentioned it, but maybe I didn't say enough about what you might call one-sided limits. Yes, I did. I used the notation. That if you're coming in from the right side, you will write, for example, so let's turn that so you can actually see it. So we want to talk about the limit as x approaches some value a from the right side of f of x. And we want to talk today about the limit that as x approaches a from the left side f of x. And these are called one-sided limits. Okay? And I think that if I go through a few examples, I think it's going to make some of your homework questions a little more clear. So we're going to try and do that. Let's see.
I think if part of it could have, for me, it could have been that error.
Okay, for the one. Well, we'll try the other one and see. But if I go back to this, here's the fact you need. The limit exists, the limit as x approaches a exists, if and only if, and the way to read that is the right-hand limit has to equal the left-hand limit. As I come into a from the positive side, it has to be the same as if I come towards a from the negative side. Okay? That I'll do, but not yet. I thought maybe some of these example functions would be a smart thing for me to do with you. Okay? I have 3 nice examples here that can be helpful. Okay? So this first function, I don't know that you're familiar with. Okay? It's called the greatest integer function. But I'm going to go ahead and use it as my first example. So, how does it work? Well, when we write this symbol in mathematics, f of x equals, and I'm going to have double bracket of x, okay? It's called the greatest integer function. But basically what it means we're supposed to round down. You guys know the difference between integers and other real numbers, right? Like if I give you the number 3.2, is that an integer? No. What I'm going to do is I'm going to put that 3.2 in these brackets, and what it means is I should round down, because I want to spit out an integer. So what's the greatest integer of 3.2? It's 3. Or if I said, what's the greatest integer of 17? Well, that is an integer, so it's 17. If I said, what's the greatest integer of 89.6? What is that?
89.
Yeah, that's 89. That's what some of you were trying to get around when you were talking about your grades earlier. But no, that's, right? This is greatest integer. It means round down. Even if you're above 0.5, you still round down. You guys follow this? Okay, what I'd like to do is I'd like to sketch a graph of this function and think about what it would look like. So if I were to graph the function, well, when I don't have a graphing calculator that has the function on it, which I'm not sure if yours has it or not. I think it may, but you'd have to find it. What you do is you probably make an input-output table, x and y, which is going to be the greatest integer of x, okay? And what you do is you pick some values. So I'll tell you what, I'll start with 0. What's the greatest integer of 0? It's 0, right? What's the greatest integer of 1? Well, this is kind of boring, right? I mean, the only time it gets interesting is if you put in some kind of a decimal, for instance. So, for example, if I put in 1.5, what's the greatest integer of 1.5? 1. And so now I have maybe a mark right there. Matter of fact, you put in 1 point whatever you want, and what's the output? 1, right? And so if you think about what this would look like, wouldn't it be true that you'd have like a line going like this, even at 1.99, until you got where? Now I'm going to put an open circle here. At 2, 1, if you want, there's an open circle, because then at 2, 2, I have a closed circle, because it jumps. And then if you go along 2, 2.2, 2.3, 2.4, those outputs are all 2 until you get to where? 3, and then it jumps. Do you guys see the pattern? This is also sometimes called a step function. A step function. And so if I go with this, I think I can safely explain to you what I mean about some of these concepts, okay? A couple things I want to say about this function. This function is not continuous at where? Give me a place that it's not continuous, that you'd have to pick up your pencil to draw it.
1.5, 2.
Well, like at 2, we just saw that, right? At any integer. Okay? It's not continuous at any integer. It is continuous at the other points. Now, when I say it's not continuous at any integer, I really need to give you an example of that, okay? So, suppose A is the number 2, okay? Now, f of A, which I'm saying is the greatest integer of 2, what does that equal? 2. So f of A is 2. But now what I want to do is I want to compute some limits. So I'm going to compute the limit as x approaches 2 of the greatest integer of x. But I'm going to do something. I'm going to put a little plus sign up here. And that means what? Approach it from which side? That means from the right. And if I put a minus sign here, that means approach it from which side? From the left. So if I approach from the right-hand side, right, I'm right here. This is the point 2, 2. The outputs are all equal to 2 if I'm coming from the right-hand side. But what about the left-hand side? All of these outputs are equal to what? What is the limit as I come in from the left-hand side? Well, the limit is represented by that circle. How high is that? Isn't that 1? Do you guys follow that?
Can you explain it again?
I'm coming in from the left side for the step function. So I'm going through things like 1.5 or 1.6 or 1. What's the greatest integer of 1.9? What about 1.9999? See, all of those outputs are 1. So the limit as I approach from the negative side, here's A. A is 2. As I approach A from the negative side, I'm at 1. As I approach from the positive side, I'm at 2. Do you guys see that? Like, what's the greatest integer of 2.4? How about 2.1? How about 2.0001? 2, right? When we talk about limits, we don't care what f of a is. We care what happens when you're close to 2. Well, it really depends which side you're on, right? If I'm close on the right-hand side, it's 2. If I'm close on the left-hand side, what's my output? 1. Those are different, aren't they? Well, if those are different, so I have to say that the limit as x approaches 2 of the greatest integer of x does not exist. Why doesn't it exist? Go ahead, question?
Yeah. So are you basically saying that when the limit from the right side, basically when you're greater than 2,
Yeah,
it's 2.
it's 2.
The other one would be when you're less than 2.
It's 1. And I can even see that from my picture here, right? Yeah, that's right. But what has to be true according to this fact that I had on the board, here, let me hit page up a couple times. There it is. The limit exists if and only if the left-hand limit is equal to what? The right-hand limit. You need to have that. If you have that, the limit exists. Okay? And then to go back to, is this continuous? See, since the limit does not exist, well, therefore, this greatest integer of x is not continuous at x equals 2. That's what I would say. Or actually at any integer, because you're going to be having 2 different values. But if you pick a fraction, it will be continuous there. You won't have to pick up your pencil there. So that's one of the ideas of continuous. Okay.